Assalamualaikum dear students. My name is ASIM'S, lecturer chemistry at Spanish Peshawar. Okay dear students, हमारा आज का lecture that is based from the first year chemistry course chapter number 7 chemical equilibrium, and that is a lecture number 2 from this chapter, and the topic is the types of chemical equilibrium. You remember the students in the first lecture related to the chapter number 7 chemical equilibrium, we discussed about that what is a chemical equilibrium, what is a chemical dynamic equilibrium, what are the reversible reactions, and we'll pick some example of that chemical reversible reaction. And also we discussed 3 graphs in the lecture number 1 related to the chemical equilibriums. So now we have to move about the types of chemical equilibrium to study that. Okay dear students, chemical equilibrium is basically are of 2 types. Look, there are 2 types. Number first type of chemical equilibrium is known as homogeneous chemical equilibrium. Chemical equilibrium. Okay, what is homogeneous chemical equilibrium, dear students? Homogeneous chemical equilibrium is basically the type of chemical equilibrium where reactants look type of chemical dynamic equilibrium, where reactants and products, you know about reactants and products, actually we discussed it in the lecture number 1. Reactants and products are in same phase. They are in same phase. Okay, what that meant? What is meant by same phase? So you people know about that the metal state or metal phase is the same thing. This same phase means same matter state. Same matter state. Either they are present in the gaseous state, all the reactants and product, either they may present all in the liquid state. But the state of the reactants and products remain same. Let for example, we have to take a few examples of the homogeneous chemical equilibrium. So the examples are, look, number first, if I write that nitrogen in the gas state, it reacts with oxygen in the gas state and it form 2 moles of nitric oxide in the gas state. And that is an example of homogeneous chemical dynamic equilibrium. Why I state this as homogeneous dynamic equilibrium? Because the reactants and the products, they are in same phase. Reactants and products will be in the same matter state. Let for example, we have to make another example like nitrogen in the gas state. It reacts with 3 moles of hydrogen in the gaseous state and it form 2 moles of ammonia, and that's also in the gas state. Again, reactants and products are in same phase. That's why that is an example, or we can call this one as homogeneous chemical equilibrium example. Okay, look, let for example, if we take ethanoate is an ester, is an organic compound in the liquid state. We hydrolyze this one. Hydrolysis of ester, we have to convert that ester by the hydrolysis, which is ester is in liquid state, water is in liquid state. It form a carboxylic acid in the liquid state, and it also form ethanol and alcohol in the liquid state. So again, you know that reactants and products are in the same phase. That's why these are known as examples of homogeneous chemical dynamic equilibrium. Okay, it's clear? Okay, look, so second type of the chemical equilibrium, the second type, that is known as heterogeneous chemical equilibrium. Okay, students. So what is a heterogeneous chemical equilibrium? So look, hetero means different. The genus B represents the state of matter. So I can write this is a type of chemical equilibrium. This is a type of chemical equilibrium where one or more, at least one is mandatory, one or more reactant or a product present in different state or in different phase. Okay, I repeat that this is a type of chemical equilibrium where one or more reactant or products they are present in a different state, and that is known as the heterogeneous chemical dynamic equilibrium. For example, we have to make some example of this heterogeneous chemical dynamic equilibrium. So the examples are, look for example, we convert calcium carbonate solid to form calcium oxide solid and carbon dioxide gas. So look, one of the product in this reversible chemical reaction is in different phase, which is carbon dioxide in gas state. That's why this is an example of heterogeneous chemical equilibrium. Look, another example. For example, sodium hydrogen carbonate is also known as baking soda. It decomposes to form sodium carbonate. It's known as washing soda, this one. It forms carbon dioxide in the gas state and it forms water in the vapor or in the gas state. That's why look in this reversible chemical reaction where sodium hydrogen carbonate and sodium carbonate is in solid state, but carbon dioxide and water vapors are in gas states. That's why this is also an example of heterogeneous chemical dynamic equilibrium. Okay, dear students, I will summarize the types of chemical equilibrium. Chemical equilibrium is basically there of two types. One is homogeneous chemical equilibrium, when the matter state of all reactants and products are same, known as homogeneous chemical equilibrium, while heterogeneous chemical equilibrium is the type of chemical equilibrium where the matter phase or a matter state of one or more reactant. Remember that at least one is mandatory, or more reactant and product is in different phase. And that type of chemical equilibrium is known as heterogeneous chemical equilibrium. Okay, let's take another concept from the chapter number 7. Okay, so look, the next topic is okay, the topic number is 7.1.2 from the textbook. Okay, first year chemistry, chapter 7, and the topic is law of mass action. The law of mass action. Okay, and with date of the law of mass action, we have to express an expression for equilibrium constant. For equilibrium constant. Okay, we will discuss that what is an equilibrium constant. So we will discuss that in the topic of law of mass action, an expression for the equilibrium constant, how we will derive the equilibrium constant for different reversible reactions. Okay, so what is the law of mass action? The law of mass action that was presented by the two scientists. It was presented by the Goldberg and that of Vaughan. These two scientists present this law of mass action. Okay, dear students, what is the statement of the law of mass action? Look, we have to look forward to the statement of this law. That what is the statement of this law? Okay, let's describe this law of mass action, which states that this law of mass action states that the rate of chemical reactions is directly proportional to active masses. Okay, what is active masses? Active masses is basically the molar concentration of the reactant substances which are involved in the chemical reaction. Okay, that's known as active masses of what? Of reacting substances in a chemical reaction. Of reacting substances. That is the statement of this law. Okay, in this law we have to cover this one, that what is an active mass, and the second one, because this is for reversible reaction, so we also pick what are the reacting substances. Okay, dear students, active masses basically it represents molar concentration. You must remember this one, that it's represent the molar concentration of the reactants or product, either in the forward reaction, either in the reverse reaction. Okay, in the lecture number 1, we also discussed that what is a forward reaction and what is a reverse reaction. So hope so that you people must take that what is a forward and what is a reverse reaction, and how you identify in a reversible chemical reaction that which one will be forward and which one will be a reverse reaction. So active masses basically means the molar concentration. Okay, what is concentration? Concentration is basically that's equal to number of moles divided by volume of substance is known as its concentration. Number of moles by volume is known as concentration. And what is the unit of concentration? So look, what is the unit of mole? Mole has a unit of mole, and volume has a unit of dm cube or meter cube. So for concentration we will write as unit mole per dm cube. Okay. So what are reacting substances? Let for example we have to take a general equation. Let for example a reactant A, which has a number of moles A, it reacts with a B reactant with a number of moles B in a balanced chemical equation. It forms product C with a small letter C with represent the number of moles, while it forms D as well with the number of moles D. Okay, remember the small letter we represent here. I first of all write here. This represents the number of moles. This also represent moles. This also represent moles. And this one also represent the number of moles in the balanced chemical equation. Okay, so look, in the first lecture we also studied that when you move from left to right side, this process in a chemical reaction will be counted as a forward direction reaction. Okay, which reaction? Forward direction process in that reversible chemical reaction. So for the forward reaction rate, chemical reaction rate, the reacting substances are A and B. These are reacting substances. So in the forward reaction rate, we will actually discuss these two reacting substances. But if we move to the product side and we discuss there, the reaction also move in the reverse direction from right to the left side. Then this process is known as reverse process. And for the reverse process, the reacting substances will be the C and D. So look, I can write it as look, that the rate of forward reaction, rate of forward reaction according to this last statement, is directly proportional to the concentration of reacting substances. Concentration is represented by the square brackets like A and B in the square brackets. Molar concentration are the active masses. Okay. While rate of reverse reaction or backward reaction are a process that's directly proportional to concentration of C and concentration of D, which will raise to the power D or C. In the case of A and B, if there are more than 1 moles, then we will write the power as well. I will represent this one. Okay, so look here. Now the rate of forward reaction will becomes equal to like that. Okay, the second one. Then the rate of forward reaction becomes equal to skip the proportionality, we have to add a constant here. A constant for the forward direction reaction, where concentration of A and concentration of B, right here, A and B. While rate of reverse reaction, that's equal to a constant for the reverse direction reaction. That's equal to the smaller concentration of C and molar concentration of D. Directly related to this one. So we know about that. We all know about that. That at equilibrium, we discussed that in the lecture number 1 in this chapter. That at equilibrium, we know that rate of forward reaction equals to the rate of reverse reaction. Then the equilibrium to be reached in this process, in this reversible reaction. So if I put values of the rate of forward reaction from here and rate of reverse reaction from here, this equation, then we will get here in this one. Like if I give the number to date, and this is equation 1, this is equation 2, and let for example this is the third one. So we will put the value of RF from equation 1, the value of rate of the reverse reaction from this 2 into the third equation. So what we get, look here dear students, we have to get that constant for the forward reaction, the concentration of A, concentration of B, okay, that's equal to, for the reverse reaction, which is equal to constant of reverse reaction, concentration of C and concentration of D. Okay, so look here, if you look, these are constant in the equation, while these are variables in this equation. So we will move constant on one side, constant terms on one side, and concentration of reactants and product on another side of the equation. So what we get, look students, what we get that I will write the equation again, that Kf, concentration of A, concentration of B, that's equal to constant for the reverse reaction, concentration of C and concentration of D. So we will rearrange this one. How we rearrange this one? We will move constant on one side and the concentration of reactants products on another side of the equation. So I will get a constant for the forward direction divided by a constant for the reverse direction. Okay, I will move this one to the left side, which becomes at the denominator side, and that's equal to concentration of C. Now I will add some power here. What is the number of moles of C? So I will write C. Concentration of D raised to power D. This D represents the number of moles in the balanced chemical equation. We will discuss some example related to that. Divided by the concentration of A raised to power A, which represents number of moles. and concentration of B raised to power B, which represents number of moles in the balanced chemical equation. So look student, a constant divided by a constant. It arises another constant where we have to put in the main title of the topic expression for the equilibrium constant related to the law of mass action. So we get here, what we get here, from these two constants we get another constant, that is Kc is equal to product concentration divided by a reactant concentration, reactants concentration. That's actually known as Kc, equilibrium constant. What is this Kc? Kc is actually equilibrium constant. Look students, this is equilibrium constant in terms of concentration. In terms of concentration, that is known as Kc, equilibrium constant. In terms of concentration. So I can also write it as, look here, that Kc is the constant of equilibrium in terms of concentration of products concentration, molar concentration, divided by reactants molar concentration, reactants. And that is known as a constant expression of equilibrium. And we will write the product concentration divided by the reactants molar concentration. So along to the law of mass action, which says that the rate of a chemical reaction, either forward direction reaction, either reverse direction reaction, that will be directly proportional to the molar concentration, of the reacting substances. In the case of reversible chemical reaction, from which one we express and we derive a relation related to the constant of equilibrium in terms of concentration, which is equal to products concentration divided by reactants concentration. Okay, we have to describe this Kc, some important points related to this Kc. Okay. Students, what is Kc? So we pick that Kc is basically the product's concentration, molar concentration, divided by a reactant's molar concentration. Reactant's concentration. Okay, remember dear students, I will write some point related to this equilibrium constant, and the point number first related to Kc, that Kc is a ratio. This is a ratio. Why I call this is a ratio? Because this is a ratio of the products of molar concentration of product divided by the product of molar concentration of reactants. I use the product term, this is only for multiplication according to that of the textbook. Look, what is Kc? Kc is a ratio. So this is a ratio of concentration of the concentration of products in a chemical reaction to that of reactants in a chemical reaction, So that is known as a ratio between the products and reactants molar concentration. Okay, so this is one point. Okay, second point related to Kc, that Kc has no specific unit. Remember that Kc has no specific unit. I can't say that Kc has a unit of, let for example, a mole per d cube, or I can say that Kc has a unit of mole square per dm6. No, that's not possible for Kc because it's a ratio. And if it is a ratio, then it has no specific unit. So if I change from reaction to reaction, then the Kc unit depends on reaction. Let for example, we will discuss it definitely. We will take some example that Kc unit is based on a reaction. How they to be explained are, I will add a question mark here. How I see state that the Kc unit is based on reaction, or this is based on a reversible chemical reaction. Look here, I will take a few examples related to that. I will explain a few examples for this one. Point number 3 related to Kc. Okay. Let for example, dear students, if I write that N2O4 decompose to form 2 moles of nitrogen dioxide. This is a gas, this is also gas. If I want to express the Kc expression for this reaction, in the Kc expression for this reaction, I will write this one. The molar concentration of products. Okay, look, I will raise the power 2 because I already explained it in a balanced chemical reaction. The number of moles will be raised as power. So I will write here its power 2 divided by the molar concentration of N2O4. So okay students, look, molar concentration is to be write as mole per dm cube. You all know about that. It's square divided by mole per dm cube. Okay, so if I look to that, then this square is cancelled out with this one. And what we get the unit of Kc in this reaction, that is unit is mole per dm cube. Now this is unit of Kc for the above equation. This is unit of Kc, but only for this equation. Okay, now let's take another example. This is one example. Okay, look, I will take another example. Let for example, if I take an equation like nitrogen reacts with oxygen and it forms nitric oxide. And there is a question in the paper that what is the unit of Kc in this equation. So you have to derive, you have to find out the unit of Kc in this equation. Remember that you will first write the Kc expression for this equation. So Kc expression is the number of moles of product raised to power 2, the number of moles of reactant 1, and multiply the number of moles of reactant 2. Okay, dear students, याद रखिए कभी भी ये गलती नहीं करनी कि if there are more reactants present and you add a sign positive here. No, there will be no positive sign. There are always to be in multiply form. If there are 2 reactants, 3 reactants or 4 reactants, you have to write in multiply form. Instead of that you have to write a positive sign. Don't write positive sign here. Write multiply sign. Okay, so look, molar concentration, so its unit is mole per dm cube, concentration unit, raised to power 2, divided by nitrogen concentration, which is expressed as mole per dm cube, and oxygen, which is also mole per dm cube. So if we log to that, then this 2 is cancelled out with this one. Because there are 2 times of mole per dm cube concentration, there is also 2 times of mole per dm cube concentration. So what we get? We get here no unit. So look, the unit of Kc depends on reaction. So now it's clear. It's clear that by changing the reaction, by changing the equation, the process, Kc units becomes changed. Like in this equation, Kc is the unit of mole per dm cube, and in this equation, Kc has no unit. So the unit of Kc is only depends on reaction, while it has no specific unit. Its units change from reaction to reaction. Okay. Okay students, the next point is point number 4. This is point 1, this is point 2, this is a point 3, and then point number 4. And the point 4 is that, that in Kc expression, only gases and aqueous form or a solution form will be expressed. So what it means? It means that, dear students, that solids and liquids not to express in Kc expression. So in the Kc expression, we will not write solid and liquid. Let for example, calcium carbonate decompose to form calcium oxide and carbon dioxide. If there is a question raised that write the Kc expression for this equation, remember that don't write the solids in the Kc expression. You have to just write the gases and a solution form in the Kc expression. So we will write the Kc here. That is, Kc is the molar concentration of the product carbon dioxide raised to power 1. But you will not write this one as that Kc for the equation is calcium oxide concentration, carbon dioxide concentration, and calcium carbonate concentration. Now this one is considered as wrong because solids will not be mentioned. Solid will not be mentioned. Remember that, and liquids will not mention. Why we not mention the solids and liquid? Because it's considered as concentration to be maintained constant. देखिए solids और liquids की जो concentration है हम उसको constant consider कर रहे हैं. That's why we will not express solids and liquids in the Kc expression. So only gases will be expressed, and how we will express the gases in a solution form. So another example. These all are gases. As you already look here in this equation, either in this equation. So the Kc for this equation is number of moles of ammonia raised to power 2 divided by nitrogen's molar concentration and hydrogen molar concentration raised to power 3. Because in the balanced chemical equation, the number of moles will becomes power or becomes the exponent in the Kc expression. Also, you get this point related to the Kc. Okay, students. So the next point related to Kc, I will discuss this one. Okay, next point related to Kc. I will write here. So Kc related next point. So, okay, the next most important point related to the Kc, look here, this is another point related to the Kc. You may continue this from this one. So, you continue from this point. This is the point number 4. Okay, we will discuss here the point number 5 related to Kc. And the next point related to Kc that Kc is neither affected by change in pressure. Remember that by changing the pressure for a chemical reaction, there will be no change in the Kc occur. There is disturbance in equilibrium occur, but not in the Kc. Okay, look, second one, or change in volume change will not affect the Kc. And third one, and concentration. also neither affect Kc. Remember that, dear students, there is only one parameter or one factor which affect the Kc of the reaction. Remember that Kc is only affected by temperature change. Affected by temperature change. Change in temperature will change the Kc of a single reaction. A single reaction has a specific Kc if we maintains the temperature. By changing the temperature, the Kc definitely will be changed. But if the temperature is maintained, or if we change the pressure, if we change the volume, we change the concentration of reactants and product, there will be no change in the Kc of a single reaction occur. But if the temperature is maintained constant, by changing temperature, the Kc will definitely affect. We will discuss that in the later lecture of the Le Chatelier's principle topic, the effect of temperature on equilibrium as well as on equilibrium constant. Okay, now let's pick some other equilibrium constant. And next is equilibrium constant. Now, equilibrium constant in terms of partial pressure. In terms of partial pressure. How I will write it? Look, for example, I select the same equation that there are two reactants reacts to form products. Then in terms of partial pressure, the expression for the equilibrium, constant of equilibrium in terms of partial pressure will become this: the partial pressure of C product raised to power C multiply the partial pressure of B product raised to power B divided by the partial pressure of A reactant raised to power A and multiply the partial pressure of B raised to power B. Now this expression is the expression of the equilibrium constant in terms of partial pressure. Okay, dear students? Okay, next equilibrium constant to be expressed, log equilibrium constant in terms of mole fraction. Okay, what is a mole fraction? Mole fraction is basically represented by x, and that's equal. Let for example, there is a component A. Then it's not mole fraction is number of moles of A divided by total moles of all components in a process. So in terms of mole fraction, I will write the expression for this equation that constant in terms of mole fraction is equal to mole fraction of C product raised to power C, okay, multiply mole fraction of D raised to power D divided by mole fraction of A reactant raised to power A and multiply mole fraction of B reactant raised to power B. Okay, so this is equilibrium constant in terms of mole fraction. Okay, the last one, equilibrium constant to be expressed in log, that is equilibrium constant in terms of moles, number of moles. How we will express that for this process? So I can write equilibrium constant in terms of moles, that's equal to the number of moles of C component, C product raised to power C, right? The number of moles of D product raised to power D, the number of moles of A reactant raised to power A, and number of moles of B reactant raised to power B. So if you look to this one, then we express 4 equilibrium constant, one equilibrium constant in terms of Kc, one equilibrium constant in terms of Kp, partial pressure, the next is in terms of mole fraction, and the next equilibrium constant in terms of moles. So now dear students, for a chemical reaction we will express the equilibrium constant in different terms. If I look to the molar concentration, then the constant of equilibrium is known as Kc. If I look to the partial pressure of the gaseous substances, then the equilibrium constant is known as Kp. In the case of mole fraction is Kx, and in the case of number of moles it becomes as Kn. So okay dear students, so that's all about the lecture number 2 from the chapter number 7, chemical equilibrium. Okay, Allah Hafiz.